There we go. All right, so we finished up with Facebook's haystack system, and we recognize that the main consequence of it is it just made their system operate a lot faster, which allowed them to essentially triple the throughput of how many photos they were delivering to people without really adding any other hardware. So that's great. Okay, and the rest of this is all just a basic intro to databases. So let's go with that. All right. So, database management system is, of course, essentially a system for keeping data up to date and retrieving it when you want to. So, data could include anything like, at Facebook, photos, right? People upload photos, that's some data. What other stuff? You could construct data from what you already have. So, you might have a list of all your users and a list of all your photos, and you might maintain lists of all the users who've liked a particular photo, right? So for any photo you have, you say, here's this photo, and here's the list of people who liked it. And you reference, entries in both tables, right? The photo references the table of photos. The individual users represent the Facebook client accounts. And you might even do more advanced questions like the set of all photos posted by a particular user over the previous 2 weeks. For example, when you go to Facebook and you click on somebody's profile, right, one of the things you quickly see is a stream of their recent activity. So Facebook might have to call that, might have to say, okay, let's see what's been going on the last couple of weeks with this person. Aside from all the other, their posts and whatever, you could also see all the particular photos they brought up. So those are the kind of things you can do with databases. And again, don't get too hung up on what data is. Data is just any kind of information that the system wants to track. So for Facebook, right, users, all the user info, all the posts they've made, all the instant messages they've sent, all the photos they've uploaded, all the games they're connected to, any transactions they've made, whatever, lists of friends, all that kind of stuff, that's all data. And different applications, different businesses will obviously have different kinds of data they're interested in. So, two main flavors of databases. Number one is relational. And that's basically what we'll be talking about today. The other is NoSQL. Okay, NoSQL is a freer form. So we'll get into it, but relational databases, they provide a lot of structure, and for certain kinds of problems, they're very fast and efficient. NoSQL systems don't allow a lot of structure. And the trade-off there is they can actually operate faster under certain cases as well. Sometimes when you don't need all that structure. All right, so we'll get into it. All right, so first, relational databases. Data gets stored as a hierarchy of tables, rows, and columns. Okay, so I have an example here. This is a table. Okay, this is a table of people, right? Whatever sort of system there is, we keep information about them. We have names, we have emails, we have password, we have birthdays, ... We have a bunch of other stuff, and then we have a link to their profile picture, right? However, that's stored in data, stored in their system, that reference. Okay, so this is a table. Table holds all the kinds of stuff, right? A particular kind of stuff. In this case, system users, and you'll notice that for every row, they all have the same kind of columns, right? So every individual in this table is called a record or a row. Those terms are interchangeable, and every row has the same kind of data, right? So if you're in this table, you have a name attribute, you have an email, you have a password, you have a birthday, and so on, and you have a link to a profile picture, okay? That's the basic structure of a relational database. And then different kinds of data that you want to keep, you keep in different tables. For example, you might have a separate table for photos, and a separate table for instant messages, and a separate table for any recent posts you've made, things like that. Okay, so data gets stored as a hierarchy of tables and rows. Table is a set of records of a particular type. A row or a record is a particular thing of that table's type. So all records exist within tables, and every record references a particular thing. So if you have a table of users, a record is one user. If you have a table of photos, a row is one photo. Okay? And then columns, or called fields, are the attributes stored for each record, right? For example, you might have a database of photos, and in that information you would have the size of the photo, the location, like what device it's stored on, and who originally posted it. You might have stuff like that, okay? Or for a user, as in the following slide, name, password, profile picture, whatever. But every row has the same set of columns. That's a basic thing of relational databases, okay? So each table is composed of a set of rows, and each row in a table has the same set of columns. Questions? This is if you're a little bit backlogged here, then it's going to get worse. This all makes sense? Okay. So here we have an example, which we've already gone through. All right. Now, what can you do with databases? Well, the 4 basic operations: insert, delete, modify, and query. So, an insert operation adds a new record, right? You can see if you're Facebook and you have a table of users, some new user wants to join Facebook, you got to create a new record in your table of users for that person, right? That's an insert operation. You can have a delete operation. Somebody says, bye-bye Facebook, I'm through with all your bullshit. And they say, please delete my account. Well, yeah, Facebook will eventually delete that record. That person no longer exists. So you need a delete operation for that. Modify. Modify is changing some data within a record. For example, you're a Facebook user, you say you reside in Chicago, but you're leaving UIC and you get a job, I don't know, in Seattle, so you move out to Seattle and your location changes, and you reflect that in your profile. That's a modify operation. You don't delete the record, you don't create a new thing, you just change the value of one or more attributes. And last, a query. Query is retrieving data. For example, you're a Facebook user, you want to see your entire list of friends because you can't remember if somebody's your friend or not. So you click on your own list of friends and blurb, you get like several dozen friends on the first screen, right? That's a query. You're asking the database a question and getting a response. Now, queries are especially important because most databases read a whole lot more often than they write, okay? You think of the case of Facebook, it's not very often we insert a photo, right? Maybe a typical user does like a few a day at most, right? It's not that often we delete something, right? But querying, boom, querying you do all the time. Every time you log into Facebook and you do anything, right? You get your feed, that's a query to the database. That's a whole bunch of, hey, what all's been going on in the world with my people? You pull that. And if you look at a particular person, you look at their profile, boom, that's another query that brings back a bunch of results, okay? Queries are where most of the work happens in databases, and so most database systems are designed to support very fast reads rather than very fast writes, okay? It's okay if it takes a second or two for some action to get processed, like you upload a photo, but what Facebook really wants is somebody goes to Facebook and they're looking around for stuff that's going on. They want that to be super fast because it gives a better user experience, and to do that, the queries have to be fast, okay? All right. In relational databases, queries can involve multiple tables, right? So obviously you might see, from this thing, pull all the records of people whose birthday is January 1st, 1962. You might run a query like that, okay? Or pull all the records from the list of users of people who are friends with me somehow. You could do that, but again, queries often go across tables. For example, you might say, retrieve the complete set of photos viewed yesterday by users from Chicago. Database admin people might do that. Now, Facebook, this is not really going to happen. Not in this kind of structure, because this is actually kind of a complex query to do. This is just an example of a query that could span across multiple tables. So first, you have to get a set of photos, and you have to link them to individual users who reside in Chicago. And then there's the time factor as well, yesterday, right? But the two tables, photos, users, you have a query that involves the intersection of those two. You're not going to retrieve all the photos. You're not going to retrieve all photos from all users. You're going to get kind of a subset of both. Okay. All right. So the language of databases is SQL or SQL. Now, if you're old, like Professor Fife, no, that's just a fact. That's not a joke. He's old. He pronounces it SQL. Many older people do this. I'm kind of right on the cusp that I could have tipped either way for SQL or SQL. A lot of older people say SQL. But, as you might guess, it is unwise to correct people either way, right? You go to some organization and there's some crusty old vice president of data processing and he talks about SQL. You don't want to be the dickhead who says, oh, I think it's called SQL now these days, right? Don't do that your first and last day on the job. Yeah, so, okay? Some people say SQL, some people say SQL. Just go with it, okay? We all try not to interrupt people when we do that. Okay. Now SQL includes command groups for queries, for all your other things, manipulations, right? Inserts, deletes, modifications. It also has things to affect table structure, right? Managing the structure itself, like creating tables, modifying columns, the parameters of how the columns are structured. So for example, these are all text. Email, you can enforce an email that it has an @ symbol and then most likely a dot somewhere following the, so you could say, well, is this a valid email address, for example? You could test that. Birthday, you could have a standard date format. There's metadata in these tables that you can use with SQL commands. Say, make this particular part of this table get formatted this way. Okay. And there's also data control language. This is for managing permissions. Because you can imagine in a big organization, not everybody has access to all data. Right? For example, the data that the HR people have about looking at everybody's salaries, sure, that's something they could, reasonably look at. But an ordinary employee should not be able to go into the database and look at all the employees' salaries. Right? So you need permissioning as well. And SQL provides all that. Okay? So that's SQL, very briefly. We will eventually have one lab exercise about constructing queries in SQL. So we don't get too deep into it, but the idea is you have seen it. And then if you're IDS majors and you go on to take IDS 410, then you'll probably do more advanced SQL stuff. But the reality is, these days, a lot of people don't have to actually mess around with SQL as is. There are basically automated features in most cases to do that. Access, for example, you can write a query using some kind of design wizard, and once you've created that query, you can actually go to a SQL view and you can see the SQL code supporting the query you just wrote. Okay. All right. Next thing, key fields. One of the things about a relational database is you don't want any duplicate records in a table. Okay? So for example, suppose I did this. We're just gonna, can I add in an extra row here? No. Probably can. Do it. There we go. Okay, so suppose I want to add on an extra row. And I create Albert Anderson with password, there we go. Password, I don't know, XYZ PDQ, birthday 1/1/1962, and profile picture, whatever the hell that is. Okay, so okay. So this Albert Anderson, let's assume for a moment this is a different Albert Anderson from the dude in the first row. Okay, but they have the same email address. How do I distinguish between them? This is frustrating, right? We know many people have the same, name. About once every year or two, I get two students in the same course that actually have the same name. Usually a Patel or I had a Rodriguez was the last pair of Rodriguez's. Common names. You're not going to find that in the Lundquist, right? But once upon a time, a class this size, you'd be like, oh yeah, there's going to be 3 Smiths in here, for example. So common names happen. Likewise, people could share an email address, but this is a problem, right? This is a problem because if you are trying to uniquely reference a particular user, for example, somebody logs into the system, wants to change their password, you have to have a way to figure out which one of these is which. Now, the way databases do that is with something called a key field. And in a key field, let's say the key field is email, boom, okay? Every entry in this column would have to be different for any pair of records, right? You can't have a duplicate value anywhere in this key field. And that way we can ensure that every record can be uniquely identified. So if we want to find a particular user, we wouldn't do it by their name because names are frequently duplicated. We would do it by their email. And when somebody registered for the system, we would say, you know what? You cannot have a duplicate email. That violates our key field policy, right? And would result in blah, 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 blah. So that's how come, a lot of systems, they use your email address as your unique identifier. And if you try to create another account with that same email address, they'll say, nope, sorry, Charlie, can't do that. Okay? That's what a key field is, and that's why we have them. Does that make sense? Questions? Okay, so key field, no duplicates within a key field, and the point of it is to enable us to uniquely identify a record. Now, you can also have multiple key fields. For example, you might say, well, I'm going to have a unique combination of name and email. And then you could have two people with the same name, or you could have two people with the same key, but you couldn't have two people with the same name and the same email. Okay, that's what it means to have multiple key fields in a table. And we'll talk about that. The lab exercise actually covers that. You get to make key fields in your tables. Okay. So, key field is never duplicated within a table, encompasses one or more fields. So when I say if you have a multi-field key, then that complete set of fields would not be duplicated within a table. And in Access, you automatically check that your key field is unique before you try to modify something or create a new record. So if, for example, Joe at joemail.com, right, that's what he uses to create his Facebook account, and some other Joe at joemail.com goes to Facebook, tries to create an account, they're going to say, nope, sorry, duplicate email, violates our key field constraint. You cannot create a new account with that email address. All right. Also, in a relational database, records in a table may reference a key field in another table. And in that case, A is called a foreign key. Okay, so for example, we can do an example with zip code very quickly. So we might have, for example, a table of users, and in the table of users, we have last name, first name, email, and let's say zip code. Okay? Zip code would make absolutely no sense to use as a key field, right? Because most often we would expect multiple users to have the same zip code. It would be pretty common. Instead, let's say we use, what's that? I'm going to make a star here. Email will be our key field. We don't have a key icon, so I'm going to use email. Email is the star, okay? But zip code could reference another table. Oop, damn it. And for every zip code, right, for every pair here, we would have a zip code as the key, and then city and state. We'll assume it's all within the United States. Okay, so again, here, we have our little star over zip code. Ta-da! Okay? And then, anytime you cross, whoop. Okay? These are the same. These are the same thing. So, a couple of consequences of this. Number one, the field users.zipcode, right, the zip code field in the table users, is a foreign key. Okay? Not a key in users, but a key in another table. Here, zip code. Okay? That's what a foreign key is. A field in one table that is actually a regular key in another table. Okay? The technical term is primary key, but we just call them key fields for short. Okay? Does this much make sense? This is what a foreign key is. Now, why is this important? Well, for example, if you want to ask a question, suppose you want to ask the question, give me a list of all users from Chicago. Okay? You don't have Chicago in that table of users. However, city and state, right? Chicago, Illinois, I'll be super specific, okay, exists in the zip code table. So what you can do, for each zip code in users, cross-check with zip code to see if the city, state combo is Chicago, Illinois. Okay? Without getting into the details of how this works, does this make sense? This is what relational databases can do if they have connections between tables like that. Okay? This is how you run a multi-table query. Questions about this?
Can one table have like multiple fields?
Yes. Well, these both have multiple fields.
No, but I mean, same way you did it for both.
You mean could one table have multiple foreign keys?
Yes.
Absolutely, yes. For example, suppose you have a table of invoices, right? All the people that have bought stuff over the last 10 years. You would probably, in that invoice table, right, each invoice represents a specific thing. But an invoice represents a person who bought something, right, the list of items that they bought, right? So those alone would probably be 2 foreign keys. If there's a zip code, like that person's address, right, or at least for the delivery address, maybe you want to include that, you could have multiple foreign keys in a table. It would often make a lot of sense to do that. Okay? In this case, keeping it simple, just doing one. Good. Anything else? Okay. So this is foreign keys. This is why they're important. They allow you to do these cross-table queries. Okay. Right. That's weird. Okay. Other things. Relational databases generally have the property of atomicity. I mean, you can make ones that don't, but it's pretty rare that you would, let that happen. So, the atomicity property, right, atoms, like meaning indivisible, even though, we know they're not actually indivisible, but still, it means. Each database field has only one element, right? So whatever that field represents, it represents one particular thing. So for example, you wouldn't have a field that has phone numbers and holds a list of phone numbers, right? Because the question is, if you try to search for somebody's phone number, which one are you getting, right? If you wanted to keep multiple phone numbers, you might have cell phone, landline, work phone, home phone, daytime phone, evening phone, whatever, right? But you wouldn't just lump all those together into a big cluster of phones in one field, okay? Because if you do that, then there's ambiguity. You want, in a relational database, you want there to be one and exactly one correct answer to any question. So if you ask you ask the database, what is this person's phone number? There should be only one phone number. If you want it to be more specific that way, again, you should include different fields, like for landline, cell phone, whatever, okay? All right. Relational database models, again, this is a whole process called normalization, but it's pretty standard that all fields are atomic. You would not normally have a field that you somehow have to parse apart and figure out the different things that are in it. So, the idea again, anything that exists in the database exists in exactly one place. And the other thing, this makes uniform data formats possible. For example, if you had a cluster of phone numbers in one field, what could happen? There's no real upper bound to how many phone numbers you could have. You might say, well, some people have 10. Okay, we'll allow people to have 10 phone numbers. But most people are just going to list one, right? So there'd be, number one, a lot of wasted space in the database. Yeah, okay. Okay. So, database metadata. We mentioned that before. Metadata is data about the data. And metadata within these kind of databases we've talked about, typically names of tables and columns, right? The database is going to run exactly the same regardless of what you call the columns, regardless of what you call the tables, but you have to give those tables names. So that's metadata. Other stuff, the type of data in a particular column. For example, you can have numbers, you can have integers or floating points, you could have times, you could have dates, you could have unformatted text. You could have text formatted in specific ways like long date, short date, phone number, 5-digit zip code, 9-digit zip codes, whatever. Okay? So formatting is the main point of what metadata is for, but again, names of tables and columns as well. Okay? Other standard design practice, any column in a relational database will have not only be present for every record in that table, it'll also use one single format throughout. Now there's other kinds of databases that relax that, but in general, right, what we would do, let's go back a few slides. So for example, name. We know that people's names have different length, right? We're not going to do something weird like say you can only enter in the first 15 characters of your name. And if you don't have 15 characters in your name, we're going to stretch it out to 15, right? That wouldn't make sense. What we do instead is we say, this name field can hold 30 characters. Okay? And if it goes longer than that, well, then it gets truncated somehow, gets chopped off. But 30 is pretty reasonable for anything you want to do. Same for email. We might set a cap for an email address at say, I don't know, 20, 25, 30, whatever. Most email addresses are not that long either. Password, right? Typically there's a minimum and a maximum length of any password, right? Anytime you go to a website and it'll ask you to create an account, say your password has to be, like 8 or 12 characters long, whatever. Birthday, since it's a date, that can be in a very simple standardized format, will be absolutely the same for each of these. And profile picture, again, you could enforce that to being exactly the same too. So, the reason why you want to do this, so here we're going to throw in a little bit of extra content. Reason why uniform field sizes are important, okay? Suppose we have this case. Suppose we have a table in a database, and there's a last name that's 30 characters long, a first name that's 20 characters long, a password that could be 12 characters long, and what else? I don't know, profile pic, okay? And that is going to be 16 characters long, okay? This allows planning, this allows calculation of how many records we can store in a space and where to find things. Let's add on one more thing. We are going to add in what's called an auto number. I'll move this down here so I can move it later. And the auto number will be 4 characters long. Doesn't have to be very big. Provides a lot of possibilities. Okay. All right, so how much is the total amount of memory in this whole set of fields? Well, it is 4 plus 30 plus 20 plus 12 plus 16. It looks like 92. Let's say that's 92 characters equals 92 bytes. Okay, 1 byte per character. Everybody with me so far? So we know 2 things. Number 1, each row has 92 bytes, and number 2, we know the offsets for each field. So for example, if I want to find the 11th record in the database, okay, I know the first one starts at address 0, so the 10th one is going to start at 10 times 92, okay? Starts at 10 times 92 bytes, equals 920, okay? I don't have to look that up from a hard drive. I don't have to, tolerate that kind of seek time. I can just do that quick calculation in RAM. I can be like, boom, I know the auto number for this record. I can instantly look it up where it needs to be. I don't have to consult a list in any way, okay? Likewise, if I want to read the password from that record, okay, if all the data fields were different sizes, I'd have to scan through the whole record until I found the password, right? And I'd have to verify the start and stop for each field. I'd say, oh, I'm done with the last name, I'm done with first name, I'm done, and keep on going until I found it, right? I'd have to do some scanning. But if this case, since everything's uniform size, I know likewise the offset for password is 4 for the auto number, plus 30, so 34 characters in is where the first name starts, plus 20 more characters in is where password starts, right? Is 54. So password for 11th record starts at 920 plus 54, 974. Okay? You're not going to have to do math like this on the exam. This is an explanation of why it's good to have uniform field sizes. If you know what you're looking for, you can find it very fast without consulting some external list, right, on a hard drive somewhere, maybe on an external network somewhere. You can just instantly calculate it and know where to find what you're looking for. Does that make sense? Okay. So this is why uniform field sizes are important. And again, it's why relational databases are still widely used. We'll see they have some troubles, but the ability to calculate things like this quickly is very nice, and the ability to link together data from different tables reasonably quickly is also very nice. Okay. So, moving on. Metadata, conflicting data. Another problem. Databases often have dependencies, which means one value inherently depends on another, right? For example, if I'm trying to calculate somebody's age, I have to do that starting from their birth date to the present day, figure out what their age is. If I have their city and state, I know that that corresponds to a particular zip code, right? So a zip code is only applicable to a certain, any zip code will be confined to a city and state, right? So Chicago can have multiple zip codes, but any particular zip code will either point to Chicago or not, right? It won't point to both Chicago and some other city. So, if you're not careful, if you don't have some sort of absolutely secure process or avoiding human error or whatever, these kind of conflicts can arise if you have these dependencies within a table, okay? So for example, back to my image here. There we go. Suppose instead of keeping zip code in a separate table, suppose I also included city and state in this table, right? Then what could happen? Well, we know the zip code 60601 is a Chicago zip code, but suppose somebody enters in the wrong city. Suppose instead of Chicago, they enter in, I don't know, Cheyenne, Wyoming, okay? They somehow mess that up, I don't know, okay? Then there's no way to see, number one, you have to do some kind of cross-checking there in the middle at some point to even identify this. But the other problem is this. If somebody's searching for people from Cheyenne, Wyoming, they're going to find this record, which is actually for Chicago, right? Whereas if somebody looks just by zip code, they're going to find it in Chicago. There'll be some kind of inconsistency there, right? Different queries, depending on how they're structured, whether they're looking for a zip code, whether they're looking for a city or state, are going to return conflicting results. Okay, so that's essentially why you don't do that. It's better to say, okay, make sure all of these entries in this table are correct, and then do the queries, involving a cross-table query in this sort of setup. Okay. So that's just intro to the issue of dependencies, data conflicts. So again, instead of storing zip code, city, and state in one table, store zip code in the first table and use a separate table to store this combination of zip code and city and state. That way you avoid that kind of conflict within the user table. Okay, just a few more. So, questions on any of this? So, pros and cons of relational databases. Number one, they're pretty efficient when data is stable, right? If the kind of data you're storing, the tables don't change, the fields don't change, that's great, okay? And also, if the fields are homogeneous for individual objects, that basically means if they're the same, right? So all those different objects, you want to track the same kind of data for all of them, that's great, okay? And you can store data in different ways to optimize query processing speed. So these are good things about relational databases. But what are the cons? Number one, it's not flexible, right? If you've gone to the trouble of setting some complicated speed optimization system, right, about which data gets stored on which hard drives and how those hard drives are connected to your other hardware, and you change something, you change the size of one of the fields, well, remember, they're all going to be tightly packed in together, right? The kind of structure I saw with the offsets for records and the offsets for fields within records, you're going to have to go through and reprocess all of that. And you're going to have to find a different way to store your data, and you're going to have to re-optimize stuff. It's a real headache. I mean, it's easy to say, well, I want to change the size of this field. But, what if, or I want to add a new field. That's an easy one. But if you have a carefully calibrated large system, it's going to require a lot of work to recalibrate it. Second, data doesn't always neatly fit relational schema, right? There might be different things you want to track about some users versus others. A simple one, invoices. So, imagine if you had a relational database with a table of invoices, right? Every invoice, what does it represent? A user who bought some stuff on a particular date, right? Well, some users might only buy one thing. Some might buy a basket of 100 things. You're going to have to allow space in your relational schema, right? You're going to have separate fields for as many purchases as somebody can buy in a particular purchase, which means there's going to be probably a lot of empty space. If one person once in a while buys 100 objects, but most people are buying nothing, or most people are buying just one or two things, you're going to have to allow space for all 100 items, but most of that's going to be empty space, right? Because most people aren't buying 100 items at a shop. Okay? Like I said, relational schema aren't always suitable for this. And last, there was designed to run on single servers. So if we're doing, short version is, if you're trying to do some cross-table query, there are certain cases where basically, in order to achieve it, basically you have to multiply the two tables together, in a sense. And without getting into the details of what that means exactly, this is IDS 200, basically means if you have one table with 1 million records and another table with 1 million records, you might be able to easily store those 2 million records on one machine, but you can't store the cross product of all those 1 million times 1 million records on one machine. You maybe don't have enough space for that, right? That's a trillion records. Even if each one is only 1 byte large, that's a terabyte. You just can't do it. And so what happens if you try to run those kind of queries across machines, instead of having the operations happen at RAM speed, like instant fast, instead you're bouncing back and forth to the different hard drives at mechanical speeds, and instead of taking, a few microseconds for each comparison, you're taking several milliseconds. So your speed could be slowed down by like a factor of many thousands. Okay, so this is how come sometimes you'll read industry cases where businesses will say, wow, it used to take us like literally a whole week to run some big queries on our machines, but then we optimized it, sent it off to Google's big query system, and now we get the results back in like 10 seconds. That's the reason why. Better organization of the data. Okay, so the alternative to that is a NoSQL system. Okay, so there's some examples. Mongo is one for document storage. Dynamo is Amazon's cloud. Cassandra is what Facebook was originally developing to allow people to search their inboxes. These are all for cases where data doesn't have one specific single format, right? So for example, documents, simple case, some are very short with no images embedded, might be like, 1K or less. Others could be very large with many images embedded, could be like several hundred megabytes. You don't want to have to try to manage the offsets. If you have to allow for a gig of data for every record, again, you're going to have a lot of dead space. So different database styles to help compress that better. Okay, we'll talk more about NoSQL systems, but this is just an idea. This is the kind of data these handle, data with less structure. They do a better job of that. Last one, Hadoop. Anybody ever heard of Hadoop? You have? All right. You've heard of it. It's real. I'm not just making this shit up. Okay. So what Hadoop is a big data number crunching operation essentially. And there's a lot of, basically tools within under the Hadoop umbrella at this point. But the basic one is something called MapReduce. So let me give an example. And then we'll call it a day. So imagine if I have a very large text document. It doesn't even have to be a text document. Suppose I have a very large table of invoices, okay? And I want to find all users, all purchases from Chicago users between September 1st and why is September so hard to type? September 30th, 2018. Okay? That's the query I want to run. Now, if this table of invoices is very large, right? Suppose we have, several terabytes of data. If I try to do this on one machine, it's going to take a very, very, very long time, right? If you've ever tried to search through this much, if you see how long it takes to search through a big table on Access, just like several megs, but several terabytes, much, much longer. I might not even have, I probably don't have the RAM to do that on a single machine anyway. So, what can we do? Well, the simple answer, number one, slice the big table into, say, 10,000 slices, 10,000 segments. Number two, send each segment to a separate machine. Do the query on each segment separately. Takes a few seconds instead of, a very long time, because much smaller slice of data. Okay? Then four, after all segments have been separately processed, recombine them and return the results to the user. Okay? That's the idea with MapReduce. You have some giant pile of data that you can do into slices, where basically the sum of the queries on each slice is going to be equal to the sum of the queries on the whole big pile, on the single query on the whole big pile of data. So you slice it up, you do the operations quick on like 10,000 machines in parallel, and you return the results about 10,000 times faster than you could if you tried to do all that processing on one machine. Does that make sense? This is a kind of thing that you can do. On a relational database system, operations at this scale are very difficult. You have to break up the data, do different things with this. This is a simple big data problem. Stuff that, you need a special dedicated system to handle because there's so much data involved. Okay? Cool. Well, that's the end of this lecture. We will come back next week and we will talk about Facebook's newsfeed.